So hi everyone, I'm Shahan and here's Vahe. So together our capstone project is titled the feasibility of scientific balloon navigation using angle and speed control. So scientific balloon has so many purposes and it's used for variant industries. For example, for aerial monitoring, for the weather analysis and multi spectrum imaging can be also installed, and so on. But so this system right here can reach up to 50 kilometers in the altitude, which is the layer stratosphere. The only ones can reach the rockets and the satellites. The rockets are so complicated systems, and the satellites are so much expensive than this system. But this system right here has so much disadvantages. First of all, when the it can easily drift by a small wind, and you can lose the control of it. So this is where the project is. So this is where our project it changed the game. We have designed a system where we can choose the x and y coordinates, and the balloon can go accordingly. So this means we can adjust the mid layer, the mid layer projection, and by that it can another application it can be used, such as the balloon-borne UAVs, which we can initially start not from here, but from the points that we want. So starting from the shape, so those balloon has a lot of shapes, and they all originate from the spherical shape. For this specific project, we have used the natural shape because it's the best for this application that we are going to reveal now. For the stress level that we have, this is the best solution. But for our MATLAB and simulations and calculations, we have used the spherical change. The spherical change. It's because of the simplicity and the physics behind it. So the forces of all of the systems are these following. So we have to access this vertical line. We have the buoyancy and the weight. When we first launch the balloon, yes, this force is much greater than this force, and that's what makes it to start the launch. And for the horizontal forces, we have this drag, which is related with the speed of the wind in squared. So the wind is very important in our system. So our design is composed of this. It has two subsystems: the angular control and the speed control. The angular control is done by this decoupler and the reaction wheel, and the speed control is done by the fixed motor. The angular control is this decoupler is an active system in which it separates the balloon from the balloon from the gondola. Yes, because some forces may affect the on the rope the torsion, and this can just ignore it. And we have the reaction wheel, which faces the gondola to the desired direction. And for the next part, the motor we choose the brushless motor, so that it generates the thrust. And go on. So as I mentioned, the wind is very important in our system. So we want to minimize the wind. But we don't have the continuous data for the real wind in different points. So the best result that we came up with was this function in the MATLAB, where it gives a small approximation. You just have to put on your coordinates. In our system, like we chose to be here in Armenia, in Yerevan, and especially, and we have plotted depending on the day, the hour, the time, and we have started from 3 kilometers up to 7 kilometers by 1 kilometer increment. From 0 to 3 kilometers, the wind is unpredictable. So we don't consider this in our MATLAB solution. And here we can, as we can see from around the day 200, the wind is at minimum, and that comes about late July. And for the timing, it's also important at what time do we fly. It's usually at nights are most windy, but as you go up with the altitude, the wind is more or less stable. And it also changes the volume, the volume of the volume by the altitude. So when we first started to launch this, it was about 4.5 meters, the meters cube. But once it reached to our desired 7 kilometers of altitude, the gases just expanded in the balloon, and we got around 9, which is the double size of that we started.
Okay, so other things that change with altitude are, of course, temperature, pressure, and density. In reality, these three variables are interconnected. However, for the purposes of the simulation, we decided to estimate them in terms of altitude. So as you can see, the temperature is a linear function, while the pressure and the density are exponentially decaying. This makes it so that the buoyancy has a minimal point for which the maximum altitude is reached, where the buoyancy and the weight equalize and create the equilibrium such that the balloon stays at one altitude. So the maximum altitude, after getting the maximum altitude, we can calculate three parameters of the balloon: the volume of the balloon, the gondola mass, and the thrust of the motor that we're going to use. The volume is in terms of the gondola mass and also temperature, pressure, and density. And the thrust is in terms of volume, which is derived from the drag equation, such that the thrust is higher than the drag at that specific altitude. However, there is another parameter, the motor mass in terms of thrust, which doesn't have a concrete equation attached to it. However, we decided to model this equation by using real-world motor data, finding the motor mass in terms of thrust through this. On the left side, we can see the real data where each point is a different motor. And as you can see, it's not perfectly linear. We decided to linearize this data by using a substitution, after which we got a linear regression model and got the slope, which is A in this equation. Okay, so we got all three equations. Now we can start the optimization process. We start with an initial condition, which is here the gondola mass. That is fed into the initial volume of the balloon, and after which we get the thrust. So this is an iterative process where each increase in the previous variable also increases the subsequent variable. So if, in fact, the series converges to a singular solution, then such a system can theoretically exist. If it diverges, then the wind speeds are too high for such a system to exist. In our system, we see that the values converge, so the system exists. So we talked about the parameters. Now let's see how the system is going to be controlled. We decided to use PID controllers, two PID controls, one for the motor thrust and one for the angular control. However, the angular control lacks the integrator portion because the integrator portion was leading to a lot of oscillations and something that is called error integral wind-up, which further disturb the angle control. So we decided to remove it. However, we should note that the two different controls, the speed control and the angular control, work independently. So the motor control only sees the distance from the desired point, while the angle control sees only the desired angle. So now we can start with the simulation results. So here the altitude is 7 kilometers, where the wind is pointing roughly in the positive y direction. And the initial conditions for these simulations are all the same. They are all at the point 0, 0 with initially 0 velocity and pointing towards the positive x direction. In the first simulation, the balloon is tasked with going to the positive x direction. So the wind pushes the balloon upwards, after which the balloon corrects itself and goes to the desired position. In the second one, the balloon has to go along the wind direction, after which it overshoots and then comes back to the desired location. And finally, in the worst case scenario, the balloon is tasked to go opposite to the wind direction, which it also is able to do as well. However, it is much slower than the other cases. To really test the rigor of our system, we also used disturbance calculation. At each time step, a random value between 1 and -1 was added to our wind to see whether the balloon can function in these harsh conditions. In the first example, it was only 1 meter range, and you can see that the balloon stays roughly within 20 or 30 meters from the desired location. However, when we put it to be plus minus 2.5 meters per second, the balloon has some offset from the desired location. However, in these harsh conditions, it also is able to stay at a concrete location and not fly away, which is actually very good since such a problem is very rare to happen in real life. Okay, so to conclude, we got a successful modeling of the balloon physics and controls. We developed a working simulation and a control algorithm. In the future, we want to find a fully automated system to be able to pre-calculate every aspect of the balloon flight. And we would love to incorporate solar power into our system to power our motors, which is very battery heavy. And finally, we would like to also validate our findings with experimental validation. All right, before ending the presentation, I would like to thank Dr. Kocharyan for his help and endless support throughout this year. And also our thanks go to the engineering faculty for teaching us throughout all these 4 years. And of course, special thanks to Ms. Satanik for helping us organize this project of Capstone. Thank you very much.
Okay, first question is the same as for the previous platform. Are you aware of a similar project or similar projects that took place in Armenia, design, flown, etc.? Have you seen anything like that?
Yes, we have heard about them, but it was not controlled. Like as I explained, it's like the first very classic model where it's like altitudes and try to get the data and that's it.
Yes,
So this is the first time that we're gonna do The control systems of it.
it wasn't, that one wasn't controlled, but there was a similar project for altitude control, and that one is flawless.
Oh, it's not the altitude control. It's the X and Y coordinates control.
Yeah. And second question as well, have you calculated the sail function of the balloon? Whether the balloon, that the motor with the battery that the balloon can carry up, actually that motor with the propeller can actually drive the balloon. Do you understand?
So you're asking if
move that balloon through the air with the
battery
motor
on it, yeah.
and the battery that it is attached to the gondola.
Yes. I don't really understand the question himself.
He says if we add everything, the motor, the battery, will be it able to fly.
Yeah, it will.
Are there any calculations around that?
Of course. Yeah. There are. Which part would you like me to derive?
So which type of battery and which type
Oh.
of battery?
We haven't considered that part for the specific mass calculations and, for example, mass calculations for the battery. We take coefficient of multiplied by the mass of the motor itself. So let's say we want a battery which is 2 times heavier than the motor itself. We just multiply that such that it is equivalent to like 3 motors on the gondola itself.
How do you do the thrust vectoring?
Thrust vectoring?
Yeah, I mean, you know, you're at a constant z and you want to move in x and y, right? When it takes it this way, you want to come that way. When it takes it that way, you want to come this way.
All right.
Your
So
position.
You don't have the rigid connection to the balloon, right? You have the Yodi coupler,
right.
which keeps your gondola independent of the balloon movement. But when you have thrust on your gondola, it's invariably gonna move through the air, and the movement of the balloon will be dependent on what you have there.
We calculated a bit on the tilt of the balloon, right? That's what you're asking. So in the given 7 kilometers altitude, that is not such a big problem since the buoyancy of the balloon itself is high enough for the tilt to not actually matter as much. But with higher altitudes where winds are higher, this is an actual issue that could arise. For lower altitudes, this is not a problem.
If you are at neutral buoyancy altitude, yeah,
Yes.
because at your target altitude, your buoyancy is neutral.
Yes.
Thrust at gondola will invariably move gondola relative to your balloon. So it is a function, and definitely your thrust vector, if your gondola is moving relative to the balloon, your thrust vector is not going to stay in the same plane.
Right.
Okay? So Oshin is asking, and I'm asking, how you are controlling your thrust vector.
And the pitch movement, right? I understand correctly.
You know, right now what you're doing, if I'm not mistaken, your balloon is a single point mass with a thrust attached to it. All forces are acting at the CG, right?
Yes.
In a
However,
balloon, all forces do not act at the CG, especially your thrust. So
we
that's
might
the
have
question.
some sort of imbalance in that
Yeah.
case. It might be tilted like this. At the desired location, we can basically say that the wind is constant, therefore the drag is also constant, which means also that the thrust as well is constant. So we will have a tilted balloon, kind of, where the drag pushes the balloon this way and the thrust is pushing it this way. If such a problem is actually found experimentally to be very difficult to handle, we can also have a swivel for a gimbal system or for the thrust itself, so it's always horizontal or opposite to the drag.
We will just go to the graphic with the linear regression.
Linear regression.
So here, I don't see what is on the y-axis. What is there?
This figure.
Yeah, both they are the same, right? The other one is just practical.
Right. On the y-axis is the motor mass,
One.
and this is thrust to the power of 1.2, which we found by manual tweaking. So we tweaked this graph so that it's linear, which we found it works well with 1.2.
So the non-linearity there is coming from what?
Sorry.
In the first graphic, the non-linearity is coming from.
It's the real data for some different types of the motors.
Okay. And the other one, the right one, is simulated.
No, this is the real data that we found. This is linearized version of that data, where we put the thrust at some power, so that the data itself follows a line, so that we can do a linear regression.
Okay, so the idea was just to make it more simple, the model.
Right.
So along the lines of what Aram said, if somebody follows up with this next year, if that's the if.
They should. Based on the result that is there, they should. Someone should.
Yeah, and I think there are, for example, Bazuk has actually flown something at 15 kilometers, if I'm not mistaken.
30.
30 kilometers. So it'd be interesting to actually get some collaboration.
It was a
between-
very interesting collaboration with Cosmo when they started the program.
Yeah.
This is around the not UAV club and also the aerospace club that we have at our college. So yes, we are aware of that. There is no
Fantastic.
collaboration at this point, but
Very
hopefully.
Yeah, it'll be great to actually, it's a very small ecosystem to get the people in that small ecosystem to kind of work together. Fantastic.
Alex has questions here. Alex?
Yes. Very good work, guys. My question is related to your assumptions. So I know you're taking into account, as Oshin also mentioned previously, the point mass distribution and all forces acting on this. But even given that, have you considered trying to basically non-positional error to determine the speed of the thrust and then some heading angle difference, right? Am I correct with this assumption?
Yeah, we used distance error
So
and
have you considered adding corrupting those measurements with some variance of noise and seeing the effect of such corruption on your control algorithm? Because if you actually implement this, so that's not taking into account any more or less simplifications, but corrupting the measurements that feed into your controllers with some variance noise to see their effect, because that would be closer to a real sensor. Have you considered that?
right. We have considered a small portion of that. However, we assume that, for example, we know that GPS, for example, has like a 5-meter error, for which we were going to use an IMU to calculate a better model of the exact position that was necessary for desired location, and also the position of the balloon itself. And hopefully with this more accurate data, such a problem cannot happen. Yeah.
So Alex, just a few words. No, we didn't. Obviously, that's a good question, but like it requires most likely filters, like Kalman filter probably. We didn't touch it at all.
Okay.
But that's more practical problem. Yeah. So that's more a practical problem, which at this stage wasn't really important for us.
Okay. Very fair. Thank you.
Thank you.
Thank you.